Hey there, machine learners. So far we've been dealing with cases where our features have been discrete. So presence or absence of traits, as was the case with the Bernoulli distribution, or categories of things. So we modeled words using the categorical distribution. However, it's also easy to imagine circumstances in which we'd like to use real valued or float valued features. For instance, perhaps we'd like to predict whether an animal is likely to survive the winter based on its length or weight. And to do this, we need a distribution over real valued random variables. And we'll talk a little bit about where this particular probability density function comes from, or this distribution comes from. But the default kind of de facto standard model for real valued random variables is something called the normal distribution, which has probability density function. We'll talk about what that means here in a second. P of x, where x is some real valued random variable, given parameters mu and sigma squared, is equal to 1 over square root 2 pi sigma squared e to the negative 1/2 x minus mu quantity squared divided by sigma squared. And if you plot this as a function of x, it looks like this. I'm sure you've seen something like this before. So here's x, here's our random variable, here's p of x, and it looks something like that, like a bell curve. That's where the name bell curve comes from. And note that this is a probability density, not a probability mass, because there are an uncountable number of real values. So the probability of drawing any particular one is going to be 0. The PDF gives a probability when integrated over a specified interval. So it'll give you an actual probability if you say, what's the probability that I draw a value between these two lines, for example. But it's not that important to us, really, what this distinction is here, because Bayes' rule and all the other stuff we talked about still applies in the same ways to these probability density functions, but there is a little bit of a different interpretation. So you should try and check yourself if you say, what's the probability that x equals 0.243? Well, it's 0. But the probability density could still be 0.243, and that's okay, and it still preserves things like order and all these other nice properties. So just keep that in your head. And so this normal distribution, sometimes called a Gaussian, it's got 2 parameters, which is a bit of a distinction from a Bernoulli, right? So we're modeling one feature here, just as we did with the Bernoulli, and the Bernoulli only had 1 parameter, which was theta, which is the chance of success of a random coin flip or something. The normal has 2 parameters. The first one is what we're going to call mu, and mu is the mean. Right? It's just the center of this distribution. We can change mu, and we can shift this bell curve to the left or the right. And then, of course, there's also this parameter sigma squared, which parameterizes the width of this distribution. So how likely is it to draw features, or draw numbers that are far away from you? How far can you get from you before it becomes very unlikely that you would draw a number further? So they basically control the location and the scale of this thing. And we can, given data, if we want to fit a distribution like this to some data, we can do it pretty easily using maximum likelihood estimation, just like we've seen for the Bernoulli. The principle ends up being exactly the same. So let's imagine that we've got you know, P of some set of observations, call them big X, given mu and sigma squared. Well, that's just going to be equal to the product over all of these observations. So 1 over square root 2 pi sigma squared e to the negative 1/2 xi minus mu squared over sigma squared. Cool. So basically, just as before, what we want to do is we want to find the mu and the sigma squared that maximize this thing, which means taking the derivative and setting equal to 0, and then solving independently for mu and sigma squared. And as before, we don't want to deal with this product, taking derivatives of this product, because that's hard. And so what we would like to do is take the log, and then it becomes a little bit more tractable. So the log likelihood for this thing is going to be L, which I'm using to denote the log likelihood, the thing that we want to minimize, is equal to some I equals 1 to m of negative log 2 pi minus, oh, sorry, and there's a 1/2 in there, minus 1/2 log sigma squared minus 1/2 x minus mu, xi minus mu squared over sigma squared. So that's the log likelihood function for the normal distribution. And if we take the derivatives of that with respect to the parameters, so dl d mu, set it equal to 0, and then solve for mu, it ends up being pretty easy to do. You'll find that the maximum likelihood estimator for the mean, call it mu hat, is equal to just 1 over m sum I equals 1 to m of x sub I. Pretty simple. What do you call this? This is the mean. So it's kind of an interesting symmetry, actually, that the maximum likelihood estimator for the normal distribution ends up being essentially the same as the maximum likelihood estimator for the Bernoulli, right? For the Bernoulli, the value theta is the mean of the data. For this normal distribution, the mean mu is also the mean of the data. And then we can do something similar for sigma squared, the variance, this sort of the width of this distribution. And what we find is that sigma squared is equal to 1 over m sum I equals 1 to m of xi minus mu squared. And so this thing inside the sum is always positive, which means that sigma squared is always positive. So the sigma squared is always a positive number. And it's basically, it gets bigger as when there are observations, data points x sub I that are far away from mu. So that behaves more or less how we would expect, that the spread in the distribution should be big when observations are far away from their mean in general. And you've seen this thing before, this sigma squared. And in fact, if you take the square root of it, you'd get a different quantity that you've surely heard of before called the standard deviation. Okay. So that's kind of all there is to the normal distribution. I mean, it's this really common thing. And once again, we'll explore a little bit where it comes from in class. But for our purposes, it's going to be useful to think about how we can use this thing. And so what I'd like to share here is how you might use the normal distribution in the context of a naive Bayes classifier. And in particular, I'm going to use the same example that I gave earlier, which is perhaps we'd like to predict whether an animal is going to survive or not based on its length. And fortunately, there's this really nice data set that you can find called the lobster data set. And here's what it looks like. Basically, in the first column of this data set, you'll find a set of lengths. And these are individual lobsters that have been measured. So we can look at this thing data. This first column is lengths, so 27 centimeters, 30 centimeters, 33 centimeters, and so forth. And then the second column is just a binary label based on whether the lobsters that were measured and then tracked survived over some fixed period of time. So this is a data set that relates lobster size to lobster mortality. And if we plot histograms of these data sets, you'll see on the x-axis is the lobster length, so spanning 25 centimeters up to 60 centimeters. 60 centimeters, pretty big lobster. And then on the y-axis, this is probability of survival as computed via histogram. And so you see that there's a pattern here, right? Like larger lobsters were more likely to survive. And so the question here then is, can we use this in the context of a naive Bayes classifier? So we might like to know the probability of survival, or probability that the lobster survives, some random variable survive equals 1, given length. And of course, we can do this quite straightforwardly given Bayes' theorem to put it in terms that we can manage. So probability of survival given length is equal to probability of length given survival times prior probability of survival, well, prior is important, divided by the probability of length. So as before, we can tackle each of these components of Bayes' theorem in a sort of component-wise manner. So first, let's look at probability of survival. So this is a random variable that has one of two outcomes, so 1 or 0, success or failure, and we know how to model that. We model that as a Bernoulli distribution with parameter theta. And of course, we also know how to compute the maximum likelihood estimator for that value theta. We just look at our data and we look at all of the observations of survival or not, and we take the mean of that thing, right? So there we go. I've just fit a Bernoulli distribution to this survival data. Theta ends up being, let's see, 0.49. So basically 50-50 actually. So this prior is not going to matter a whole lot. But then what we also want to do is fit this probability of length given survival. And here's where that normal distribution is going to come in. We're going to model length as a normal distribution given these two different populations of lobsters. So we'll actually fit normal distribution, two normal distributions, one to the lobsters that died, one separate normal distribution to the lobsters that survived. And so they'll each have their own mean and variance associated with them, right? And so here's my function that I've defined that calculates the maximum likelihood estimator. I think you'll agree that this is equivalent to the maximum likelihood estimator that I wrote in the whiteboard just a minute ago. And here we go. We can just use these functions to compute these mu's and these sigma squareds for the class of lobsters that didn't survive and the class of lobsters that did survive. Easy enough. And now that we've computed them, we can have a look at the resulting probability density functions, or these bell curves applied to each of the lobster classes, right? So here's my likelihood function. This is just that PDF. And if I evaluate this PDF for these parameters that I learned and plot them as a function of length, you'll see that I've now fit this bell curve. It sort of winds up with these histograms. But this is my model of length given class, right? So my lobsters that died have a mean length of 37 or so with a standard deviation of 10 or something like that, which translates to a variance of about 100 since it's squared. And similarly for survived, we've got a different mean and a different variance. And so I could, draw random samples from this distribution, or I could do whatever with it, but we're gonna plug it back into Bayes' theorem to help with this process of classification. So let's do that now. We can evaluate Bayes' theorem by saying the post, which I'm using as the variable to store my posterior distribution over survival, is this posterior, and this posterior is just likelihood with the survival class parameters times the prior with the theta that I learned divided by the evidence, because I want like a true probability, and the evidence is just based on these parameters that I learned as well. So we've got all the information that we need to evaluate Bayes' theorem here. We can do it. And now we have the posterior probability of lobster survival given length. And we can plot that. It ends up being kind of interesting, this shape. So we have the same histograms that we saw before of lobsters dying versus surviving. But then this right axis, which is the additional axis, is the posterior as a function of length. So probability of survival as a function of length. And so you see this sort of S-shaped curve that goes from, 10 centimeter long lobsters are not likely to survive to kind of a 50-50 chance here, where the two normal distributions end up overlapping with one another. In fact, if we plotted those normals again, you'd see that to almost certain survival for large lobsters. And of course, we could apply a threshold to this curve in order to explicitly classify new lobsters into the two different classes here, but that's kind of throwing away information. It's actually oftentimes really interesting to know these actual probabilities. Okay, so that is the Bayes classifier applied under a circumstance where our features are no longer either categorical or Bernoulli, but are instead real valued and modeled with a normal distribution. And critically, we can go one step further here and actually generalize this normal distribution to modeling not just scalar values like length, but to modeling real valued vectors. So for instance, let's say we had two features representing length and weight. Well, if we then say for one of these two classes, if we just looked at the survive class or so, we might have a data set that looks like this, right? With a bunch of dots. So instead of just measuring a lobster's length, we also measured its weight. And this is what we get for one of those two classes. So if we then write the vector x equals length and weight, then we could write probability over there we go. Probability over the vector x is modeled by a multivariate normal over the vector x with parameters mu, which is now going to be a vector, and covariance matrix sigma, which is a matrix. And so the mean is still pretty intuitive for this multivariate normal. It's still going to be just the middle of the data set. You know, now since it's a vector, you can not just move it right or left, but you can also move it up or down because instead of a 1D parameter, we've got this or 1D data, now we've got this 2D data set. But that's not a big difference. But now we've got this thing, this covariance matrix here, which is just a little bit richer in its behavior than the univariate normal distribution's variance. So, you know, we can write sigma is equal to this matrix. And on the diagonals, we've got sigma squared length and sigma squared weight. And those still correspond to the width. So, you know, if we looked at the projection of this data set onto these axes, this width would be sigma squared length. This width would be sigma squared weight. But then there's this additional thing that can appear on the off diagonal. So we'll call that sigma LW. And a covariance matrix is symmetric, which is useful because it means that this thing and this thing are always going to be the same. They're symmetric. So that's good. And it also helps to keep the number of parameters that we'll have to infer a little bit low. But what does this thing mean? Well, what does this off diagonal thing mean? You can sort of think of it as related to correlation between these two variables, right? So if we were to draw some lines on this graph representing contours, like a contour plot of the probability density function of the normal distribution, if we didn't have this off diagonal term, we could only draw like circles, basically. We could draw circles such that the axes of, or ovals, I guess, such that the axes of these ovals were oriented with the axes themselves, which is essentially an implicit way of stating that length and weight are independent. If we just draw circles, it means that the probability density over weight doesn't depend on the probability density over length, which might be a bad assumption, but that's basically what we would be saying if we ignored these off diagonal terms. And what they allow us to do is to basically draw more nicely fitting ellipses to this data set, ellipses that allow for length and weight to influence one another's values and to be dependent, which is oftentimes very useful. And this has a cost, of course, in the sense that even though we've only got 2 random variables, each of which, if we were modeling them using univariate normal distributions, would have 2 parameters each, right? A mean and a variance. But in this case, now we've got a vector of means, a 2 vector of means. So that's 2 parameters. These variance terms for each of the features independently, and then also this this covariance term, and that's a total of 5 parameters rather than 4. So that's the extra expense, is that now we have an additional parameter to estimate, and sometimes that'll be prohibitive, sometimes that'll be really useful, and we'll see in the days to come when we might want to make different assumptions about whether or not to include that term. So that's all I've got to say about normal distributions for now. We'll return to this a bunch of times, but this is just a first introduction to it.